Thank you for downloading the Start the Week podcast from BBC Radio 4. For more information, go to bbc.co.uk/Radio 4. Hello. I've learned some intriguing things this week. It hadn't really occurred to me, I'm ashamed to say, that you can get 3 right angles into a triangle until Ian Stewart showed me how. One of the simpler challenges in his new book, 17 Equations That Changed the World, a celebration of the mathematics that lies buried just beneath the surface of everyday life. I didn't know either about the significant role the billiard ball played in the development of cinema until I watched Mark Miodownik's television series The Secret World of Materials, which sets out to reveal the invisible magic behind a lot of the stuff we take for granted. Also on the programme this week, the sculptor Peter Randall Page, whose work is inspired by the mathematics of the natural world, and Jane Rapley, head of Central St Martin's College of Art and Design, who takes a special interest in material at the cutting edge. It's not impossible that one day we won't be buying a new winter coat, we'll be growing it. We're starting, though, with equations, that point where the truths of the physical world find expression in mathematical symbols. And if you're feeling nervous, take courage. Ian Stewart, the author of 17 Equations That Changed the World, has won 3 gold medals for his work on the public understanding of science. Ian, you acknowledge that equations are scary in the introduction to your book, but I think I'm right in saying that the starting point for this book is a mild sense of grievance that equations don't get their due.
I have a lot of sympathy with people where their heart sinks into their boots as someone mentions the word equation. And I don't think equations will ever be sort of cute, cuddly little creatures that we all learn to love. But mathematicians love them, and they have reasons for it. And what I wanted to do, it's the old show business adage, if you've got a wooden leg, wave it. If people don't like equations, let's actually make those the focus of the whole book. So I wanted to show people not the stuff that puts us all off, which is how to solve it, how to do quadratics, how to do all the things you have to get dragged through with mathematical technique, but the background to it, which I think makes the whole thing much more palatable. Where did they come from? What are they for? And what have they done for us, both historically and in everyday life today? Every single one of my 17 equations is something that, in fact, in some gadget you're carrying around, or something in your kitchen, or something that is happening to you almost every day, deep down inside it, buried underneath, is one of these equations.
You use the analogy of writing a book about mountaineering. You say you can no more write a book about mountaineering without using the word mountain than you can write a book about equations without including equations. I did get the sense as I was reading it, you start with the foothills. Pythagoras' theorem, I really was okay with that. I was much better than I expected with logarithms too, and I'm grateful to you for that. After that, you start to get to the Alpine peaks, don't you, and the Himalayas. Why is that progression of difficulty? Is that just that we gradually learn more and more, and so we're reaching higher peaks?
It's a mixture of things. Historically, as time passes, the mathematics behind the equations gets more sophisticated because we're learning more. And I think people today are no more intelligent than they were 2,000 years ago, but we have this huge cultural capital that people like Pythagoras started, or indeed continue. It goes back to the Neanderthals, I would think, but there's this cultural capital has built up. And so it was kind of natural that the equations would progress in depth and difficulty. It was to some extent unavoidable. There's also a good principle with a book that you put the easy stuff at the beginning to suck your readers in, and then you leave the hard stuff till the end, by which time they've already bought the book and they're committed. And each of the chapters historically overlaps. So, I take an equation, I take it through 1,000 years of history, and then we go back 800 years to get to the next equation.
And how did you settle on the 17? Because obviously you could have had 35, presumably, or many more. What was it that narrowed it down?
Mostly what narrowed it down was the need to get it into a normal-sized book. But basically, I started out with about 20 or 30 equations. They were biased towards the ones I actually knew about. And there are many areas that have not been touched on at all. And, there may be 17 more equations that change the world would be possible.
That's volume 2.
That's volume 2. And we ended up with about 20. And then I started thinking, what I need to do is combine together related equations and use one of them as a kind of icon for all the others, so that I can then get everything into one chapter. So special and general relativity in this book all come from E equals mc squared, the famous Einstein formula, which is actually not the most important formula in the area at all, but that's the peg on which I can hang the discussion of relativity and modern physics.
It's not complicated to see from a layman's point of view why E equals mc squared became so widely known, because it's so simple. Now, for mathematicians, presumably something different attracts them in an equation. You talk of love and you talk of beauty. What is it that makes an equation beautiful for a mathematician? Symmetry is a given, isn't it?
Yeah. I think for a mathematician, what makes an equation beautiful is the simplicity of the equation, but in the sense... Simplicity to a mathematician can mean, crumbs, that's complicated to everybody else. It's simple within the context of what you understand. So one of my favourites in the whole book is the wave equation. And if you write this as a mathematical formula in modern notation, it's only about 3 symbols. I mean, it's very, very compact, beautiful equation. But the beauty of it is that this compact expression, as you unfold it by looking at the solutions of the equation, suddenly a whole world of interesting patterns and phenomena open up. So the wave equation, it explains sound waves, it explains light, it's where radio and television came from. The fact that I can speak to people on the radio today, historically this is because physicists discovered and mathematicians discovered the wave equation in the theory of electromagnetism. I thought, well, there must be electromagnetic waves. That's radio.
You're very good in each chapter on the practical consequences, so that you always find out what the practical applications of these equations are, what they open up, the areas of the world. It's not always a good thing. I mean, some of these equations change the world for the worse, don't they? I was very interested to read about black skulls, which is the equation at the heart of the financial crisis. Could you just explain a little bit about that?
This is an equation which was devised by 2 economists, Fisher-Black and Myron Scholes, who put together, actually it's a very beautiful equation, and it's how to put a sensible price on a financial option, which means an option is a contract to buy or sell goods at some point in the future for an agreed price. It's a kind of insurance originally.
And did they become enchanted by it? I mean, that's the other thing that you get throughout the book, the sense that an equation is a talisman. And if you forget what lies behind it, you can be blinded by it.
Yeah, I mean, this is a wonderful equation. It created a $250 a year industry, which is 100 times the...
quadrillion bubble, as it's also known.
It gave people confidence to buy and sell financial instruments instead of commodities, and then to buy and sell instruments that were secured on other instruments, and sort of bets on bets on bets on bets. I was reading today about derivatives of credit default swaps, which are themselves derivatives. This is getting very, very esoteric. But the formulas gave people the confidence to trade them, and until it all went, until the market conditions changed, it was working quite well.
Mark Meerdovkin, can I bring you in here? I'm taking it that you're familiar with equations and at home with equations, and
yes, I mean
you don't feel the general public alarm at them.
No, I mean, material scientists, in the 20th century, we started to understand materials from a physical and mathematical perspective. And what's amazing about materials is that actually they were sort of designed by accident. They were sort of invented by the arts and the sciences all throughout history. And it's only later that we've understood the equations for instance, steel, or for plastics, or for wood, in fact. But I was, there was a slight disappointment as I was reading your book to find that not one materials equation was in there. I mean, you might argue that Schrödinger's equation is the ultimate materials equation because it describes the behaviour of atoms, and so, of course, you can't get more fundamental than that. But
we're smiling round the table at the notion that your favourite equation didn't get in.
It is, I'm afraid. I mean, Thomas Young, he's a polymath, one of the last person who knew everything. He's got this great equation which involves the Young's modulus, which describes elasticity. This is what makes materials squidgy or not. It's what means that buildings are rigid, or your elastic underpants stick to your body.
Can I just ask a very crude question? In a lot of these cases, the equation has predictive power, but it's also just a description, isn't it? It's a description after the effect. You know something does something, and then you write down a mathematical description of it.
Yes, usually the equation comes from observations. So somebody notices something, like Kepler noticed that planets move in ellipses, and then Isaac Newton says, there's an equation which predicts this, and also it will predict much more complicated things in planetary motion.
So it'll point forward as well. Peter Randall Page, you're looking at your art. You wouldn't think of equations, but you might think that an equation might be derived from it in some cases. There's a symmetry to it and a pattern to it.
Yes, that's right. I mean, pattern, I think, is a often misunderstood term in many ways. I mean, people think of pattern as something kind of superficial, almost like a sort of decorative add-on to things. But of course, once you start looking at the world carefully, you realise that pattern is absolutely fundamental to everything. And of course, mathematics is the study of pattern fundamentally. So I think, many, many years ago, even in childhood, I started to be aware that there are actually a fairly limited sort of pattern book, almost, of geometric form.
That's the other great seduction of equations, isn't it? The idea that you can simplify and that beneath the massive complexity of the world.
But then you look at the world and you think, my goodness, it looks like a completely, almost infinite variety of forms with very little repetition, in a sense.
Jane, I just wanted to ask Jane Rapp, I'm guessing that an equation never passes under your gaze from one year to the next, but maybe I'm completely wrong.
No, you're right. I'm part of the sort of the general public where you say equation and I start rising panic, really, as to.
I'm sure there is, and somebody will one day work out and publish in the paper the equation for the connection between skirt length and economic. I mean, there is that odd passion for equations, isn't there, which the popular press feeds with bogus equations. Does that irritate you?
It irritates mathematicians. I mean, there was a genuine one, which was the biscuit dunking equation, which is actually quite a nice equation about the flow of fluid through a porous material. Yes, but then you start to get silly ones.
Yes, no, I remember one for beer goggles. I think somebody had done an equation for beer goggles, which seemed a bit far-fetched.
There was some analysis of skirt length and economic prosperity, but I can't remember the precise connection.
We'll have to come on to it later. I want to move on to Peter Randall Page, and we're sort of connected here more than we would normally be because of the degree to which mathematics shapes your art and the degree to which you're interested in it. And
Sure, yeah. I mean, I suppose that the thing about this underpinning of everything by pattern is that also you have this equally ubiquitous tendency, it seems to me, in our universe for random variation, and it's that combination of those two. And in a way, those polarities, you could almost see them as the driving force behind the evolutionary process itself. Because if we only had pattern, this tendency for spontaneous pattern formation, we wouldn't have any development or change or variety. If we only had random variation, well, one can hardly imagine what that would be like. But the combination of those two things, and I've become interested in exploring that and actually, having really been inspired and informed in my work by an observation of natural phenomena generally, not being a mathematician but just getting interested through experimentation and observation of things.
Does any kind of mathematics, because you look at your works, for example, there's a beautiful piece, and I suppose one shorthand description of it would be that it's like a Platonic BlackBerry, but perfect. You couldn't have a Platonic BlackBerry, I don't suppose, but that's what it is, and it's beautifully symmetrical, geometrically very finely detailed. So is any kind of base level maths involved in making that, the actual process of making it?
The process of making it a little bit sometimes, because one uses techniques like triangulation, which was known by the Egyptians and very, very linked to
Pythagoras.
Yeah. And that's a very, very good way of locating points in space. If you've got three known points, you can find a fourth point. But that is just a sort of functional thing in terms of being very useful when you're trying to understand three-dimensional form. But in a way, as an artist, what interests me particularly about pattern is the fact that we are above all, pattern recognising creatures. And so we are looking for pattern and meaning all the time, everywhere, even where, we're even trying to find meaning where there is no pattern. I mean, if you think about the stars, I mean, apart from the planets, this really is a random lot of dots of light in the air, and yet we make them into Ursa Major and Ursa Minor, and this isn't pattern in a sense, but it's trying to breathe meaning into our world, which is what we do. And I think what's interesting is if you have ambiguity, then our tendency to want to find pattern and meaning tells us quite interesting things about the human condition, about actually what makes us tick. And that's, of course, what I'm interested in. I'm not interested in stone as such. I'm interested in what making sculpture can tell us about the human condition.
But in some cases, this isn't a randomly applied pattern, is it? It's not just the viewer perceiving it to be there. You've got a lot of works which use the Fibonacci series, and that way in which pattern emerges from the simplest of rules. And if you apply it and repeat it and repeat it, you get the most beautiful.
Absolutely. Although, you see, I think when you describe the sort of geometric blackberry, or however you described it, I mean, that is probably less mathematically and symmetrically correct than you think. I mean, we are ourselves not perfectly bilaterally symmetrical.
Yes.
If you actually do that thing of taking a photograph and flipping it over so you make the person look completely symmetrical, they look weird. It looks like some alien. You can't even put your finger on why.
So you mean looking at that piece of work, I'm mentally refining it?
I think to some extent, and of course with lots of things I make, I deliberately introduce a random element. For example, using a glacial boulder which has been shaped by the dumb conditions of erosion over thousands of years, and then combining with that some sort of geometric construction.
Well, what's very lovely is that random form is then netted within.
Well, and of course
the
geometry has to give and morph and change in order to accommodate the randomness. And the trick, as far as I'm concerned, is to also have a space between those polarities of an ordering principle and a random variation, where one can then actually improvise and play and invent in rather the same way that a jazz musician might invent on a theme, because of course variation without theme is meaningless, and we have to have structure in order to create a playground for us to explore our psychological feelings.
You're very wedded to stone in particular, and I think you've said that you wouldn't work with wood. Why is that? Why is it that stone?
I mean, I think stone, in a way, I mean, people do find it quite difficult to understand why on earth in the 21st century one would be making things out of stone. For me, it's fundamentally stuff. It's what the earth is made of. It's also solid, and most of the things we deal with in our everyday life tend to be kind of hollow boxes. We have rooms, we have houses, we have vehicles, we have wardrobes. All these things are hollow boxes. And there's something rather amazing about that dark, dumb interior
and
of,
the density
solidity,
of it.
the density of it. You ask about wood. I mean, wood, the other challenge, I suppose, with stone is that we think of it as a very dead material, particularly igneous stone like granite. And the challenge, in a way, of imbuing it with some human meaning and some vitality is far more than, for me, working with wood, which, of course, already has these, the residue of its structural things which were created by growth. So it already has an organic history.
Jane Rapley, we're on much more familiar ground here in terms of pattern, particularly. I mean, I kept on looking at some of the work you've done, and you see them almost as fabric patterns, and the deep attraction of that. What is it about that overlay of pattern over organic form that works so well? Perhaps that's not a...
Well, I think it goes back exactly to what you're saying. Is actually we as humans actually want to give shape and structure to what we look at. What we then do often, of course, is to destroy it, depending on what messages we're trying to tell ourselves and what condition we're in. And you often see this, and we talk about how we interrelate with ourselves and what messages we're telling ourselves and what our society wants to say about ourselves. So we frequently destroy and then we reform. And
do you mean you disrupt pattern?
Yes, you
create
disrupt
it and then disrupt
yes,
it.
and disrupt it for messaging, for purposes, because we're, I don't know, frustrated by something, or angry about something, or bored with something. And I mean, it's interesting because you've talked about the symmetry and its beauty. Often we get to the point where we actually get bored with that, and we actually have to disrupt it.
Well, as you were saying, the pure symmetry is rather eerie and
yes. I mean,
unliving.
bilateral symmetry is a particularly interesting case psychologically, I think. You know, and, an example of that is the classic sort of Rorschach, ink blot thing. I mean, when you immediately look at something which is bilaterally symmetrical, it starts to, it mainlines into the emotional part of our brain, I think, which is why that was used. And I think there's a very simple reason for that, is because we ourselves are pretty much bilaterally symmetrical, not perfect, as I said, but and it goes into that sense about feeling, we're so good at reading expression into the human body and the human face.
Mark Meadowlarkin.
Yeah, I was fascinated by this sense of playfulness and a discovery of an inner world from your sculptures. This idea that they're like a massive boulder, which is an acorn, which you've cracked open, and inside is this wonderful pattern. And I think from a material science perspective, you don't expect pattern at that scale in anything that size. Like, as you were saying with the stars, if you look out to the big things in the universe, and a boulder is a big thing, really, and so's a mountain, so's a galaxy. There's very little pattern. It's boulders are boulders, mountains are craggy. If you want to find natural pattern that forms, you have to go round to the microscale. So the fact that
I'm sure that Ian can give you an equation for the pattern of a mountain range. But
this is very interesting about life as well, and pattern and scale being associated with certain sizes of things. And you've created these things that are outside things that you should never have those patterns, and your brain recoils. It never has seen anything. It knows fundamentally that pattern shouldn't exist, and then you've created it. Which is marvellous.
It's interesting, that scale thing, because I almost think sometimes that there are these sort of layers of scale. If one looks at the very big scale, if one looks at the universe, incredible patterns of planets revolving around stars and so on, which have very, very strong and strict patterns. Then you go through other areas where things start to seem rather chaotic, as you say, like rock formations and so on.
Ian Stewart.
The word scale chaotic rock formations instantly
you
remind
can't
me.
say that to a mathematician, can you?
Fractals. This is patterns that are actually independent of scale, or in a sense, the pattern is how things look the same on different scales. So if you take a rock and a small rock or a big mountain, and you look at them, you put them on the same scale. So you have the rock right up close to you, the mountain is way over in the distance. Quite often it's very hard to distinguish the two. A Swedish friend sent me a photograph which shows one of his friends in a boat leaning on the bank of the river, except the bank of the river is actually a cliff about half a mile high of a fjord. And you can't tell the difference in the scale. And this kind of scale independence is at the basis of fractals, which are a new kind of mathematical pattern.
I'm going to move on because you said you take a rock, and it's the perfect cue into Mark Meadowlarkin, whose television series, The Secret World of Material, starts with you taking a rock and splitting it open. I mean, your first programme is about metals, and it begins with this almost magical discovery that brute stone could be transformed into something else. Did you? The question I want to know: did you actually sit out there on the heights and smelt your own copper?
Yeah, I mean, we flew out to the original place, Timna in Israel, where our ancestors first discovered that these rather greenish bluish rocks could be transformed into copper, into metal. And we tried to recreate that moment. Now, of course, that isn't something that's very easy to do on the spur of the moment, especially with a TV TV schedule, I have to say. But we made progress, and we kind of found little bits of copper, and I dragged them out of the ashes, as you can see in the programme. But it is such a magical moment because you're surrounded by rock. The world is essentially made of rock, and to discover that out of that rock has hidden secrets, that you can make the stuff metal, which then completely is the basis for our whole civilization, is really extraordinary.
You use the word magic a lot. Actually, there's a very lovely moment where you show off memory metal that can reform itself into the proper shape, and you say that is indistinguishable from magic. I take it that was a deliberate quote from Arthur C. Clarke, that any sufficiently advanced technology is indistinguishable from magic.
Yes, I mean, we live in a world. If you look around yourself now, anyone who's listening to this program, look around you now. You are in a wonderful world of materials that we've created, and each one of them is a miracle, is a revolution in its time.
But your point is that, as it were, not even advanced technology, that's magic too. We should be looking at a spoon and being amazed.
Absolutely. I mean, a stainless steel spoon, I mean, if you're having your breakfast now and you put it in your mouth, you are not tasting almost anything. Now, we are the first generation not to taste our cutlery. Almost every other metal is strong tasting. Almost every other material is quite strong tasting. It's quite hard not to taste the thing you put in your mouth. The stainless steel is genius. And the thing that's stopping you tasting it is actually an invisible layer that self-heals. Now, you wouldn't believe it, but that's...
And that presumably was an accidental discovery, that they found that out after making stainless steel and thought, oh, terrific.
It's one of those, yes, I mean, the history of materials discovery, as I was saying before, is a history of accidents. It's only relatively recently that we've got to grips with the theory of materials and the physics of atoms and started to design our own from scratch, as it were. So the discovery of stainless steel is a lovely one. It's in Sheffield, and they're looking to try and make harder metals for gun barrels, would you believe it? And they're just adding alloy element after alloy element into iron because they know that alloying things can make them harder.
That's what's fascinating, because the trajectory of your programmes, I mean, the first one, it's very clear that failure, and often catastrophic failure, is a big engine for advancement. You have the Tay Bridge disaster, which moves us on from cast iron. You have the comet, the failure of the comet, which teaches us things about metal fatigue and so on. But there's this continued sense that this is a process of accidents, of trying it and seeing whether it works and then trying something else. Are we not moving now to a point at which we can literally, atom by atom, say, look, we've got the computing power. If we put these two things together, I'm pretty sure this is what's going to happen.
Yes, I think that is what's happening now, and that's terribly exciting. I mean, Jane will tell you that, fabrics are being designed now that are literally out of this world. We'll be able to do things that we can only dream of a few years ago. And so there's these things called nanotechnologies, which is literally putting materials together atom by atom and understanding the processes in which they interact with each other. And that's a relatively recent science and is opening up not just huge possibilities, but, of course, ethical and societal issues that we also have to address. And I think that's the challenge of new materials in the future, is to bring the whole society around these, what are going to be a whole revolutionary set of materials.
I just want to ask you about the billiard ball and film, just in case people are intrigued by it, because I thought it was a delightful little anecdote. So just explain that. This is genuinely part of the have a go and see what works.
Yes, I mean, it's the American Civil War. Everyone's into billiards in America, and they're running out of ivory, and it's a very expensive material, and they have to sort of kill elephants to make it. And so they have a competition to replace ivory for billiard balls, and people all over the country try and make up different ways of doing it. And this guy called John Hyatt invents a kind of plastic, and it's sort of prototype plastic, and he's very excited about it, except that when he deploys it, in these saloons, they find they explode and burst into flames when they hit each other, and that is the birth, as you said, of celluloid, which is a flammable material, but did in fact, it's one of those amazing things where materials discovery ignites a whole new industry, which is the cinema.
Yeah, rather literally in this case, it ignites.
I just wanted to pick up on the Arthur C. Clarke quote about technology and magic, because there's a variant on it which Gregory Benford, the physicist, put into print a while ago, which is, any technology distinguishable from magic is insufficiently advanced. It's an imperative, and it's exactly what Mark is talking about with nanotechnology. The whole idea of technology is to hide all of the hidden, all of the secret rules that make it work. So it's like a stage magician who doesn't want you to know what the trick is. But as a scientist or a mathematician, you are actually focused on how to do the trick. That's where the equations in our lives come from. And if I use a mobile phone, I do not want to think about the Fourier transform and the various code systems that are going in. I just want to press the switch and speak into it and talk to the person on the other end. But if I want to be in a society which has mobile phones, which sometimes I feel perhaps maybe is not such a bright idea, but usually they're very, very worthwhile. We have to have people who understand how the magic works. So this is where the maths and science lives in our society.
Mobile phones, I suppose, are something that anybody would still find a little bit magical, but I like the way you're trying to restore some magic to something as simple as wrought iron, which you do in the first programme.
Metals themselves, and we're all used to seeing them around us, these enormous hunks of stuff that we make trains and bridges out of. That is one of the most marvellous materials we've ever made. It's a miracle material, and it has, in a way, delivered the modern world. I mean, the postmodern world will almost certainly be delivered by nanotechnology and others in biotechnology, but the modern world lies on steel, concrete, and glass, which are all materials that are the ancients discovered, and we honed over thousands of years.
And we're still honing.
Yes, indeed. And the other thing I sort of wanted to talk about is what these materials mean to us, what they actually... they represent something about us. They are... If you want to know who we are, there's... you can look at Ian's book and look at the equations, but you can just look around you, and this is a reflection of who we are, our values. People's homes are full of soft things, they're comforting, because we are rather fragile creatures. They are surrounded by hard things because the weather and the planet is actually quite a ferocious place, and we've managed to create a cocoon for ourselves that allows us to be human, and it's the materials that have done that. And so they are more fundamental than perhaps people give them credit for.
Well, and some of this development is going into not sort of raw utility, but something more psychological. I mean, certainly in the case of fashion and textiles.
Yes, absolutely. But I think there's a very interesting pattern that emerges here, where technologists, scientists, engineers, inventors, experimenters begin in one place, and we then end up with we deploy it because our imagination starts to actually look at its potential. We deploy it in all sorts of different ways. And it's the issues about accidents of things like the billiard ball, which then becomes the cinema, which morphs on. And actually, I think that's where artists, designers, writers actually provide the interface with the human condition that reflects wherever we are in our society. I think the issues about materials, and I think we're at a very fundamental watershed in the sense as we move into a post-industrial society, as we move in the West, as our colleagues in Asia, probably Africa, probably South America, actually go full tilt into an industrialisation that we're moving out of, is we have to think about these materials in the long term. And certainly as artists and designers, 20 years ago, people started to begin to worry and be concerned about how we're consuming materials, what we're now doing to our society, and how we can deploy them in a different way or in a more responsible way. And I think that's where the new science and the convergence of science is really, really stimulating and interesting. Frightening, but also...
What's frightening?
Well, I think you mentioned that, we can possibly now grow clothes, we can grow materials. We can take the sort of... There's been a sort of holy grail of filament, if you like, the spider silk. There's been quite a lot in the press about it, and I think 2002 it was announced that with the genotechnology you could introduce the geno in. You could breed goats, and from the goat milk you could use the proteins to make the spider silk. 2 years ago, that's only 8 years on. You can now do it in a petri dish. And
I'm a bit disappointed that you no longer need the spider goat, but
but the goat still's got to be bred. It's got to be fed. It's still using our materials in a world where we're saying, well, we can't afford to run cattle herds anymore because they're eating too much of our natural resources. And there's a whole big question. And if we think that the public can't cope with GM crops, there's going to be a big issue about how they're going to deal with this new...
Isn't there another issue as well, particularly pointed in the area of fashion? I was looking just the other day at a YouTube display of nanomaterials which you can apply hydrophobic coating to a sneaker. And you could pour chocolate syrup, golden syrup, it would just ripple off. And it reminded me of that film, The Man in the White Suit, that famous Ealing comedy. where he invents the perfect material and industry does not want him to. I mean, fashion depends to a certain degree on obsolescence. It's built around that, isn't it? So
yes, well, that's because we're in a consumerist society. So, I mean, it comes back to what's our economic model going to be in the future as we come out of an industrial age? And, I'm not clever enough to tell you that. We probably need some very clever economists working with some mathematicians to actually produce a formula or an equation. Yes, it does. I mean, it's not just fashion. We consume, and so we consume. The obsolescence of ideas and materials is important, but actually one of the sciences is about building in obsolescence within the materials that we use.
Yes, well, I'm just wondering about this. I mean, one suspects that fashion wouldn't innovate anything that's going to threaten fashion. That's unlikely to happen, isn't it? Mark Meadowfney.
Yeah, I mean, I think nature, if you look at nature's materials, woods and the plastics that really are sort of leaves and plants and so on, and then the animals, as we've just been talking about, they do the same. But what they do is they recycle rather effectively. I don't think this constant change of material form is necessarily a bad thing. And I take your point about the economic model, but I think I wouldn't make a sin out of fashion. Definitely wouldn't. I think this built-in obsolescence, this constant need to change our appearance and how we feel about ourselves, is a reflection of how we're feeling different about ourselves. So that's fair enough for me. I just think that we need to knock on the head that recycling bit, which we are absolutely terrible at, and there is no political commitment to.
But this is where a lot of the stuff that you're, at the far advanced end, you are talking about textiles that can be composted, or textiles that can be, entirely melted down and recreated into something else, aren't we?
Yes, to some extent we're looking at that, but we're also looking at how our clothes and our environments can take on other functions as our society requires them. And we have researchers, Helen Story, who's very well known as a fashion designer who has been working with science for the last 10 years. She's got a project on at the moment looking at catalytic clothing, which actually is
just explain what catalytic.
It's a basic clothing with a coating that actually, as you wear it in the environment, that it will actually purify your environment and actually then sort of decomposes of its own volition, so that it's doing a double function. So
you are a kind of walking pollution clearing.
Yeah. Now,
device.
whether it will be effective or have any impact whatsoever, but it's about the psychology about I'm being good. I'm not being.
It might be about the psychology of I'm getting dirtier with every step I take.
Well, it might be. It might be, but it's actually about what messages we want to say about ourselves and how we're operating and living. I
wanted to ask you as well about the coat that you can grow, or the fabrics that you can grow, because it's quite an interesting. You're using cellulose material. You're at a stage now where there's quite a difficult aesthetic problem with that, isn't there? Because it looks like dried skin when you end up.
Yes, yes.
So we're in an intermediate stage at the moment.
And it's an experiment in a laboratory. I mean, it has a long way to go before it actually can be deployed in our everyday world. And maybe it won't be. Maybe what will happen is that the science and the development of genome and technology and nanotechnology will move so fast that actually that won't be the route that will be.
And is
taken.
there not a growing affection for authenticity of material? I mean, you think of the nylon shirt, not perhaps. I mean, a great step forward in materials, not a great step forward in fashion. And we've moved away from it, but
it took us on a journey, didn't it? It took us. It's this need and want relationship. What do we need? What do we want? And a lot of what happens with design, and not just in fashion, it morphs need into want, and then want feeds back into need, and it took us on a journey that results in all sorts of things. That sports stuff, and the investment, the drivers for these developments often come from military, medical, little bit sports, not from fashion, because it's too short term. The investments isn't long enough. But what it then does, what designers then do, is that they will deploy what is found for the military. NASA is a huge source of all sorts of fabrics that we are now deploying in our real life.
Well, the military have famously got silent Velcro. You know what I mean? Velcro is this wonderful material, this way of joining things together, shoes and coats and clothes and bags. It's genius, isn't it? Yes. I mean, it'll last for 20 years. You can wash it. You can do whatever you like. It's got moving parts, but they're tiny. But it makes that sound, doesn't it? And if you're in a cinema or in a lecture, that's always very embarrassing. And the military, of course, don't want that to happen in the battlefield. So they've got silent Velcro, and look forward to silent Velcro coming from the military into everyday life.
Stealth Velcro. Peter Randall-Page, I wonder what you feel about this, because your work absolutely goes back to the deep attraction of old materials. I think you have used chemicals in getting patterns for some of your work, but mostly it's just this deep reassurance of ancient materials.
To some extent. I mean, I think, the thing of having something which is which you haven't had control over its production, in a sense, as a raw material, that it's not something that's already been through some sort of human manufacturing process, is for me hugely attractive. But I think, going back to actually picking up on some of the things about fashion and clothing, I mean, this has a big relevance from my point of view in kind of perhaps unexpected ways. I mean, one of the jobs I had when I first left art college was working at Wells Cathedral on the, restoring and conserving the 13th century statuary, which is this wonderful drapery. And of course, we do spend our lives making deductions about what's inside things from the look of the things on the outside. Obviously drapery is one thing. We have skin then, and we have, that's overlaying muscle and bone and so on. So we are kind of understanding from the outside of things, and we love to use pattern in that way. People have always tattooed themselves, and I think the phenomena of the fishnet tights, for example, because they break up the leg into these increments, you actually appreciate the form more fully because your eyes slowed down.
That's
you get the quality of light and shade.
That's brilliant. I bet you've never heard a more high-minded account of a fishnet stocking, and I want the equation soon as well. Thank you to all of my guests. Jane Rapley, head of Central St Martin's College of Art and Design. Peter Randall-Page, whose two monumental sculptures, Fructus and Corpus, are going to be installed in Riverside Walk Gardens in Millbank from the end of April as part of the Cultural Olympiad. Ian Stewart's 17 Equations That Changed the World is out now, and you can see Mark Miodownik's series on the science of materials on BBC4 in the spring. Next week, Andrew Marr will be back to discuss faith and doubt with Richard Holloway, Karen Armstrong and Jonathan Safran Foer. But for now, goodbye. No more write a book about mountaineering without using the word mountain than you can write a book about equations without including equations. I did get the sense as I was reading it, you start with the foothills. Pythagoras' theorem, I really was okay with that. I was much better than I expected with logarithms too, and I'm grateful to you for that. After that, you start to get to the Alpine peaks, don't you, and the Himalayas. Why is that progression of difficulty? Is that just that we gradually learn more and more, and so we're reaching higher peaks?
It's a mixture of things. Historically, as time passes, the mathematics behind the equations gets more sophisticated because we're learning more. And I think people today are no more intelligent than they were 2,000 years ago. But we have this huge cultural capital that people like Pythagoras started, or indeed continue. It goes back to the Neanderthals, I would think. But there's this cultural capital has built up. And so it was kind of natural that the equations would progress in depth and difficulty. It was to some extent unavoidable. There's also a good principle with a book that you put the easy stuff at the beginning to suck your readers in, and then you leave the hard stuff till the end, by which time they've already bought the book and they're committed. And each of the chapters historically overlaps. So, I take an equation, I take it through 1,000 years of history, and then we go back 800 years to get to the next equation.
And how did you settle on the 17? Because obviously you could have had 35, presumably, or many more. What was it that narrowed it down?
Mostly what narrowed it down was the need to get it into a normal-sized book. But basically, I started out with about 20 or 30 equations. They were biased towards the ones I actually knew about. And there are many areas that have not been touched on at all, and there may be 17 more equations that change the world would be possible.
That's volume 2.
That's volume 2. And we ended up with about 20, and then I started thinking, what I need to do is combine together related equations and use one of them as a kind of icon for all the others, so that I can then get everything into one chapter. So special and general relativity in this book all come from E equals mc squared, the famous Einstein formula, which is actually not the most important formula in the area at all, but that's the peg on which I can hang the discussion of relativity and modern physics.
It's not complicated to see from a layman's point of view why E equals mc squared became so widely known, because it's so simple. Now, for mathematicians, presumably something different attracts them in an equation. You talk of love and you talk of beauty. What is it that makes an equation beautiful for a mathematician? Symmetry is a given, isn't it?
Yeah. I think for a mathematician, what makes an equation beautiful is the simplicity of the equation, but in the sense... Simplicity to a mathematician can mean, crumbs, that's complicated to everybody else. It's simple within the context of what you understand. So one of my favourites in the whole book is the wave equation. And if you write this as a mathematical formula in modern notation, it's only about 3 symbols. I mean, it's very, very compact, beautiful equation. But the beauty of it is that this compact expression, as you unfold it by looking at the solutions of the equation, suddenly a whole world of interesting patterns and phenomena open up. So the wave equation, it explains sound waves, it explains light, it's where radio and television came from. The fact that I can speak to people on the radio today, historically this is because physicists discovered and mathematicians discovered the wave equation in the theory of electromagnetism. I thought, well, there must be electromagnetic waves. That's radio.
You're very good in each chapter on the practical consequences, so that you always find out what the practical applications of these equations are, what they open up, the areas of the world. It's not always a good thing. I mean, some of these equations change the world for the worst. Thank you for downloading the Start the Week podcast from BBC Radio 4. For more information, go to bbc.co.uk/Radio 4. Hello. I've learned some intriguing things this week. It hadn't really occurred to me, I'm ashamed to say, that you can get 3 right angles into a triangle, until Ian Stewart showed me how. One of the simpler challenges in his new book, 17 Equations That Changed the World, a celebration of the mathematics that lies buried just beneath the surface of everyday life. I didn't know either about the significant role the billiard ball played in the development of cinema, until I watched Mark Miodownik's television series The Secret World of Materials, which sets out to reveal the invisible magic behind a lot of the stuff we take for granted. Also on the programme this week, the sculptor Peter Randall Page, whose work is inspired by the mathematics of the natural world, and Jane Rapley, head of Central St Martin's College of Art and Design, who takes a special interest in material at the cutting edge. It's not impossible that one day we won't be buying a new winter coat, we'll be growing it. We're starting, though, with equations, that point where the truths of the physical world find expression in mathematical symbols. And if you're feeling nervous, take courage. Ian Stewart, the author of 17 Equations That Changed the World, has won 3 gold medals for his work on the public understanding of science. Ian, you acknowledge that equations are scary in the introduction to your book, but I think I'm right in saying that the starting point for this book is a mild sense of grievance that equations don't get their due.
I have a lot of sympathy with people where their heart sinks into their boots as someone mentions the word equation. And I don't think equations will ever be sort of cute, cuddly little creatures that we all learn to love. But mathematicians love them, and they have reasons for it. And what I wanted to do, it's the old show business adage, if you've got a wooden leg, wave it. If people don't like equations, let's actually make those the focus of the whole book. So I wanted to show people not the stuff that puts us all off, which is how to solve it, how to do quadratics, how to do all the things you have to get dragged through with mathematical technique, but the background to it, which I think makes the whole thing much more palatable. Where did they come from? What are they for? And what have they done for us, both historically and in everyday life today. Every single one of my 17 equations is something that, in fact, in some gadget you're carrying around, or something in your kitchen, or something that is happening to you almost every day, deep down inside it, buried underneath, is one of these equations.
You use the analogy of writing a book about mountaineering. You say you can